This video includes demonstration on how to work with micro cantilever structures. This is very similar to what we did with our first experiment on macro cantilever structures, albeit we are going to deal with macro cantilever structures on a much more smaller scale to sort of study the same trends which we did in the first experiment. This is the illustration of a macro cantilever structure. I will be having a dimension of 200 is to 20 is to 2, and I will be plotting for both the von Mises stress and the displacement, and we are estimating the same graphs as we did in the first experiment. And what we're doing in addition to the same things is we are also trying to have a parametric sweep of force, and we're trying to understand for a given point if the displacement and the stress is going to vary with the varying force from 1 micronewton to 5 micronewtons. I will now start to do the simulation. Now for the initial setup, we will once again choose to go with the model wizard, which helps us to have the initial environment. I'll be clicking on the model wizard window. This leads us to the space dimension where I will be selecting the 3D dimension since our cantilever is a 3-dimensional structure in space. Now, what we will be selecting once again would be a structural mechanics. We will be choosing solid mechanics as solid, and we're adding that. We don't really have to add anything else. We're just doing a static study like we did in the first experiment. So the study once again here will be a stationary study. I double click on that, and now the interface is going to take a moment before it opens me the same geometry window it opened in the first experiment, but this time you make sure that the length unit is not meters but is in micrometers. This is because we are doing a micro cantilever structure this time. And now to make the geometry itself, I click on geometry, and in the primitives options I click on the block to create a cuboidal structure representing my cantilever beam. I am going to use 200, 20, and 10 as depicted in the 20 and 2 as depicted in my illustration. I'm going to build all objects, and this is my cantilever beam. This is as was expected in our initial depiction of the cantilever beam. Now we will follow the same procedures, but this time for the materials we will be choosing polysilicon. We will not be going with structural steel. Now, a few notes on the physical properties of polysilicon is that the Young's modulus of polysilicon is unlike structural steel, which had 200 gigapascals of Young's modulus. For polysilicon, it is 160 gigapascals, or more precisely 169 gigapascals. The density is 2320 kilograms per meter cube, and these are a few quantities which you might or might not want to remember for later on. Right now, what you want to make sure after the material is selected is you want to add constraints, and to do that you go to physics. Under boundaries you might want to first add a constraint to one end of the cantilever beam. Zoom it in if you're not able to properly select the face. And now for the boundary load, you will add it to the other end of the cantilever beam, right? But this time, once again, this would be total force. But you make sure that the force you are going to add this time is going to be in micronewtons. And the way to do that, if you see how I've depicted force here, it's 1e minus 6, right? And this is the scientific notation to depict this. It's 1 micronewton. And what this is implying is it's 1 times, when it's e to the power negative 6, it's essentially telling it's to 10 to the power negative 6. So this is what this specific line is depicting. And usually in COMSOL you have to imply or suggest this in scientific notations like I've written here. So it's always nice to be familiar with that notation. Once again, I'm going to have it as a negative z force because I want the force to act downwards to what the z-axis is pointing towards. I do 1 e minus 6, right? So that's 1 micronewtons. So now we've added a 1 micronewton force. I've constrained the cantilever at the other end. Now I can create a mesh. I can go to mesh and I can once again do a swept mesh like I did with the macro cantilever. I would decrease the size to an extremely fine mesh. So now once this is done, I can simply compute, right? And as I compute, the first thing I'm going to look at is the von Mises test, which we previously saw in our first experiment. The first plot is always a von Mises test, as you can see here. We want to have 2D plots right now, yeah? And the way to do the 2D plots is you go to results and you click on the 1D plot group. And now under that, you click on the line graph. And what you're going to do is you're going to define a cut line. Now, previously, we had always defined cut lines. Now, you can define a cut line, but you can also select from manual selection. Now, since we're estimating this to be rigid bodies, it really doesn't matter. But you can either choose an edge like this, or you can go for a cut line. They're going to give you the same results since this cantilever beam is assumed to be a rigid body, and you know that in a rigid body, given any 2 points in a rigid body, will always have the same distance irrespective of what force is acting on them, because they don't deform, right? But for the case of this study, since we've always defined a 3D cut line, I'm going to define a 3D cut line. It's not going to change anything, but why not? One end of it is going to be at the fixed point, and the other end is going to be at the free end. Yeah. So this is going to create a cut line which traverses through the section of the cantilever beam. Yeah. I can leave the displacement field of the y data as it is, and I can leave the arc length as it is, and I can continue plotting. I see a very clean and higher order plot, which is what we are expecting with the displacement. Now for the von Mises test, what you can do is you can create another 1D plot in the results, and you can add another line graph, and you can keep everything else the same. We can use the cut line from our previous study, and instead of the solid displacement expression, you can replace that with von Mises, right? And everything else is going to remain just as it is. I'm just going to click on plot, and this is going to plot a really clean von Mises test. I don't really have to cut the boundaries either. In this case, it's mostly almost clean, but I can cut the initial boundary since it's slightly distorted at the point load end. I can do something like a 0.05, and we can go all the way up to 200. Now we can see how that looks like. Um, and we can probably go like a 5 since that's not changing a lot. And at 5 it's somewhat good, but we could still go like a 10. Yeah, it looks pretty clean at 10. We could go from 10 all the way to 200, and it looks pretty nice to me. Now for the maximum displacement, you can click on the line graph, and there's the graph marker tool to get the maximum and the minimum stress value, and the same thing for the displacement, a marker again to get the maximum and the minimum displacement values. For the table, of course, you can right click on the line graph again, and you can click on plot data into the table. You could do the same thing with the stress. Now you get both of your plots. This is as was in the first experiment. What we're going to do in addition to everything we have already done is we're going to try and do a parametric sweep, right? And we're going to do that for force. Now, the way to do a parametric sweep is to go to global definitions, and what you can do is under parameters, add a name for force. I'm going to call this F naught. And the expression for force is obviously, we can give a default value for the force as 1, and I can write this in micronewtons, and that's going to give me 1 micronewton as the default value of the force. And I can go to boundary load. Now this time, instead of this expression, I can replace this with F naught, which is going to be my parameter. It's minus F naught because it's acting downwards. Now, if you don't have to do anything else, you just have to go to the study here, and when you right click on the study, you get an option for parametric sweep. Now you select on the parametric sweep, and you right click on this space here, the free space, and you click on add a parameter, and you're going to select the F naught. And the way to define ranges in COMSOL is by using the keyword range, and inside brackets you write the initial value, which is 1 micronewton, so it's 1e minus 6, and the steps at which it's going to proceed is going to be 1e minus 6, and I want it to go all the way up to 5e minus 6, right? So it's 1 micronewton to 5 micronewton, and it's sweeping in 1 micronewton steps. So it's going to give me a sweep of 5. And when I simulate for this and I'm computing this parametric sweep, it's going to take a moment there. Um, but it's going to give me 5 different snapshots of 5 different configurations. That's with 5 micronewtons. That's with 4 micronewtons. You see the plot is going to be slightly different with how much stress is happening, how much displacement is happening. And you can visualize these plots by going to results and adding another 1D plot group. Now this time, instead of a line graph, you might want to choose a point graph because we want to examine the value of force at a certain point, and usually you want to explore the maximum. So for displacement, I'll go at the free end and choose any of the points, and I'm going to choose the first data set itself. And what I'm going to do is that I'm going to do all the parameters for the f naught, and I'm going to keep the displacement as it is, but for the x-axis I'm going to choose the parameter value, and I'm going to click on plot. You see that the force, as you increase the force, the displacement linearly increases. So this is the first plot which we now wanted. You increase in force, increases displacement in a cantilever beam. So we can add that as one plot. That is, if you're going to sweep force, you're going to sweep force against something like displacement maximum, displacement maximum, you see that the trend is linear in nature, and this is verified with our plot over here. And you can of course do the same thing with stress. We can go to results, we can add a 1D plot group, and you can click a point graph again, and this time, since the maximum stress is to the edge, you can click on the point in the edge where the fixed end is present, and all the other expressions remain the same except the solid displacement is replaced, this time with 1 mesostress, because that is what we're trying to explore in this experiment. And I'm simply going to click on plot again, and you see this is also linear with increasing force. So once again, it's a very clean plot. So this is how you do primarily parametric sweep for different parameters, and this helps you sort of visualize how different variables influence different physical parameters, right? So this is a variable, force is a variable, and sweeping force, you see, there's going to be different physical parameters that vary. And you can see how these physical parameters are varying. In this case, both of them are linearly varying. That is one thing you've concluded from this study. You can vary, of course, other things, and you can still explore how that's going to change anything. And these are very interesting to use, and they sort of give you a rough idea on how a certain variable can change different features about a physical system. This is a small demonstration on parametric sweep. A few other things I forgot to explain my previous cases. Some of these things were exploring nonlinear solutions, right? Now you see there's an option to include geometric nonlinearity. So certain cases when the force is really high, that causes a lot of deformation, and the rigid body no longer stays rigid, right? Now, the linear elastic material study assumes that a body is a rigid body, but in a really strong force, there's going to be a permanent plastic deformation, so it's not going to remain a rigid body anymore. You want to explore geometric non-linearity in such situations. So if you're using a lot of force which is going to deform your solid, make sure to click on this button before you click on compute. Otherwise, you won't have a lot of good results, because the initial assumption about rigid body is no longer sustains himself. Another thing I told you about my previous study is something in physics, and in global we had included the gravity. I've not included the gravity in this section again because the micro cantilever has negligible effects for gravity. That is one reason I've just skipped over, glossed over that section. And the reason I've glossed over the non-linearity section is because anywhere from 1 micronewton to a 5 micronewton force is not going to cause a permanent plastic deformation. So the assumptions about rigid bodies are going to sustain themselves. I think this is the end for this demonstration. I think I've covered everything I promised I would. For the next demonstration, we are going to use the same micro cantilever structure, and we are going to explore two more studies. And these studies are very commonly used in COMSOL. They're called time-dependent studies, and the other one is called a frequency domain study, right? What we're going to do with these studies, in the time dependent study, we're going to do a transient analysis, right? Based on everything we studied about resonant frequencies, we're going to do a transient analysis, and we're going to study damping. And in our frequency domain, we're going to do a spectral sweep to understand the sort of resonant frequency where the displacement is going to be the maximum. This is a more primitive form of eigenfrequency analysis because we're only going to find the resonant frequency for the first mode and not the other modes. We can also find it for the other modes, but we're going to mostly sweep between the expected ranges to arrive at only the first mode, since we don't want to explore too much. These are going to be the scopes for the upcoming video. I hope you'd be tuned or excited for the next videos. If you have any feedbacks or suggestions, you can drop them by. And if you have any doubts, you can also drop them by. I hope you're having a good day. Take care a lot. Bye bye.